actually lead to contracting the clocks of the robot, given the two clock functions that we defined in the previous slide. So in our context, the trajectory x and h belong to a lattice, and their domains will be represented by tubes, which are intervals of trajectories. I'm going to present really quick what are tubes. The tube x is an interval x minus x plus of fn, such that x minus is inferior to x plus. So to represent this, we have a trajectory or a random signal x, and we have an upper bound function x plus and a lower bound function x minus, which enclose the signal. This is an assembled version of a random signal. So we can extend some classical operation. We have a function of fn, such as sum, multiplication, image by a function to choose. Okay? It suffices to say that we are going to use classical notion of interval arithmetics and inclusion function for all t. An arithmetic on tube is thus a direct extension of arithmetic on intervals. Two simple examples would be the addition and the integration. Okay? So we can also define some contractors on tubes. We define a contract with constraint L, and we define the associated contractor CL. So just like in intervals, contractors on tubes will verify the contracting and the completeness properties. This can be easily demonstrated. So we can also define some minimal contractors. For example, the minimal contractors associated with the delayed signal x of t equal y of t minus 2 is defined as follows. What this means is, for example, when we have two tubes, x and y, enclosing two signals, we are going to delay the first tube y of 2 seconds, okay? And we are going to take the highest lower bound and the lowest higher bound, okay? And this will actually contract the tube around y and x. So we rewrite our cooperative localization problem as a constraint satisfaction problem. The 5 equations, the 5 constraints I showed in part 2 are rewritten as contractors. So for all t, we have the 2 contractors associated with the 2 differential equations, and we use a forward-backward algorithm to contract the other 3 equations. So the first 3 equations are obtained for all t as their differential equation, and the forward-backward algorithm is applied each time we receive a ping from a robot. Okay. So this is, I'm going to go into detail into the equation, but what is important to understand is this figure. We have a robot inside this box, okay, robot I, that is going to emit a ping at time A. And we have a robot J in this black box that is going to receive the ping at time B. Okay? And the purple area is going to be the possible solution for the position of robot J in the intertemporal observation function. Okay? So what we see is that we can already contract the position of J since the intersection with the purple area is empty here. So we can already contract the position of J. And we can also see that we can contract the purple area here as it's not going up to the black box, okay? So in the forward-backward algorithm, this will translate as contracting the intervals around A and B, which will lead to contracting the clocks of the robots. So some test case. I'm going to show you first a little simulation I did for this. Okay, so we are going to have 2 circles, and the little red black dots are the commands that we are going to give to the robot. we want 6 robots here to follow 3 on this circle and 3 on this circle. Okay? The robots on this circle are going to be able to access the GPS around there. So you're going to see their box to really decrease around there. And robots on this circle are not going to use their GPS, they are just going to be able to communicate with the sonar ping with the robots on this circle. So I'm going to launch the simulation. And so you can see the box, the position around the robots. When you see the little circle, it's the sonar ping emitted by a robot. And when you see the red line between the robots, it means that they are in range, which means that if a ping touches them, they can receive the data. So you can see, for example, here, when the robot is going to emit, the robot that receiving can contract its position. You cannot see it here, but it's also going to contract its clock. I'm going to show you that in the next slide. So this is another little software I developed to display and compute tubes. And you can see the position of, let's talk about B first. It's going to be the abscissa of the robot. Okay? So if we use only the differential equation, the state equation, according to the noise, the width of the tube is going to increase, okay? Except if we have here a communication being received from another robot that has a smaller box, okay? This is going to contract the width of the box. And the same thing is happening for the clocks. In A, you have the clock function for a robot receiving a communication. So in this case, it's not receiving, the noise is just making the tube increase until it's receiving a communication. At this point, the tube can be contracted thanks to the forward-backward algorithm we defined earlier. This is the same thing for a longer time. We can see the abscissa of the robot and the clock function. So I made some real experiments in the sea. So this is and this is the two robots we use. I started with only 2 robots from Syskria that have vectorial propulsion. It's one yesterday. And I made the test in Brest. So you can see them in action. So I tried to do the same experiment than in my simulation. One robot is going to make some turns on circle using the GPS every 5 seconds. And another robot is going to make some turn next to it and only going to communicate with the other robot. So, okay. So this is the GPS track of the robots. I'm just showing it to you, but I'm not using them for the computation after. And this is the box, the position computed from the input of the robot, because we have the joystick to command them, and the state equation. And since in this case the robots are not communicating, the state noise may make the box increase and explode to the point that we don't know where's the robot anymore. But we're going to use some communication between the robots. We didn't have the sonar, but I simulated some communication between the robots, and when robots are in range of less than 20 meters, they could communicate. And this is a little green line that you can see. So in this case, we can see that this time the position box are much smaller. Well, this one because it's using the GPS every 5 seconds, and this one because it's communicating every time we have a green line. Unfortunately, in this experiment, it was only 3 minutes long, so the clocks of the robots didn't shift much. So, and the state noise was so big that it was impossible to actually contract the clocks of the robots. But I hope that later we make some longer experiment with a shift of a few seconds to show the contraction on the clock. So to conclude, I propose a solution to solve an intertemporal constraint satisfaction problem with uncertain time, which is, to my knowledge, something that is not easily done with the extended Kalman filter. And in the future, I would like to make more experiments with long-term experiments. and to make the algorithm robust to outlier. Finally, this is I can give you the article about that. It has been submitted to Paladin a month ago, and we'll see if they accept it. And this is the reference. Thank you.
Are there any questions?
Thank you for your talk. Very lively. You suggested some contractors for ODEs or for tube of trajectories. But my understanding is that it works only if you have a closed form solution for the ODE. Am I right?
What is ODE?
I mean the tube of trajectories.
Oh, okay. So, can you repeat the question? I don't understand what is.
Okay, so you showed you have a dynamical system, the evolution equation, and then you showed that you would write an integral form of it, and then you build a constructor.
Yeah.
So the question is, does it work when you do not have a closed form for the solution of the evolution matrix? Because it's a differential equation.
Yes. We start from the initial state. We know that the initial state was 0. So the expansion was controlled.
Yes, but you solve by hand. I mean, can
no,
you show?
I didn't solve the equation. We did some integration over the intervals. We applied some solving like some methods like a layer or Wingebuta to solve the differential equation.
So you have no guarantee. You lose guarantee.
No, definitely not.
It's an interval integration. It's an interval integration. But here in the implementation, it's
here it's a layer. I implemented interval layer.
Yes. So the question holds. I mean, it works only if you have a closed form solution for the integral.
Yeah, I guess.
I mean, it's only curious. I mean, I'm curious about the applicability. I mean, let's say you consider the chemical process that have been showed two talks prior. Can you apply your contractor? Yes? No?
Yes.
No, but it depends,
no,
because for instance, in the implementation, the addition is not guaranteed. The sign is not guaranteed. But of course, in principle, we can use any, we need to use a V-node or interval or guaranteed interval analysis, but it is not the case here. But of course, it should be done to have a guarantee. The implementation is not guaranteed.
It's not yet guaranteed.
It's not yet, but we are waiting to use IBEX on this, and of course to put some guaranteed method. But in the principle could be applied even if you have any state equation. X dot, any state equation, x dot equal f of x and u.
But can you use, for instance, the Picard operator and to have a guaranteed relaxation like this? Or?
Yes.
I think yes, because once you have large box, you decrease it because you have other constraints coming from other.
Yes, hopefully. Eventually it would decrease.
But
Hopefully.
this is the principle.
It doesn't work all the time, of course. Okay, no, that's the question. Okay.
But the GPS helps to reduce
Sorry?
Apparently the GPS is very useful to push me.
Yeah, I guess the uncertainty reduces when you can do the measurement about your actual position. Then you do not need the model, but that's a joke. But, so what kind of information you exchange between the robots?
The emitting robot emits its position box, the box you know it is in, which can be large, can be really big, or really small, we don't know. And the interval around its emitting signal. When it emits the signal, it's going to end to send, for example, 3.5, which is the interval when the sync is going to send the signal. So it's the ATIL. It's going to send the ATIL, the interval around ATIL.
Okay, thank you.
Why is it so large? Why do clocks shift so much?
Here in the example, it was a state node actually, because the model we have for the robot is not accurate enough. So we have a really big state noise. But if we had really precise robots, we would have a much smaller state noise.
The question is about the clock. Why it drifts so much? Because we think about experiment that can take years. For instance, you can have several robots. They go at the bottom, they sleep for 1 year, and after 1 year, they are not synchronized anymore. So they have to synchronize using a resolution technique.
Yeah,
But in practice, it's difficult because if you have 1 day, an experiment of 1 day, the drift will be almost zero.
yeah, that's why I couldn't show the clock contraction in the real experiment, because it was too small.
Are there any questions? I wonder how large can your swarm be?
There is no limitation.
Well, in practice, yes.
Well, in practice, yes. In theory, no, I actually begin to program the simulator with a dozen robots. In the next week, you will see with a dozen robots.
What is the technique of changing density of the object inside the water, or the robot you are using, so that it comes up on the surface and down?
The severity of the sound?
How do you change? Because
Yeah,
yesterday I
well,
said
I thought about that.
density.
I thought about that. It's easy because you just have to consider the severity of the sound like an interval, and you contract around C. Contract around the interval C.
Changing of buoyancy.
Yeah.
How this is changed?
C.
Buoyancy from remote, how it is changed of an object inside the water.
You're speaking about the salinity of the water, right?
It floats, it is inside the water, it comes up on the surface and it can move according inside the robot. So how do you change the density of the robot so that
Oh.
you told me yesterday, na? That I know. What is the technique of changing?
Oh, the robots have a zero
Directional
density.
control is
Well,
fine.
they have the same density than the water. So if you put them into the water, they are going to stay in the middle water, you know. And it's just going to be with propulsors that are horizontally shifted, and they are going to propulse it down or up. So yeah, depending on the salinity of the water, you have to modify the density of the robot. The weight of the robot.
In those robots, you have never inertial measurement units,
Oh yes, there is. But
Yeah.
we don't have to use them.
and you have no noise, yeah, because
Yeah, there is.
yeah, there are a lot of noise also, and it is also embedded. Those sensors are also embedded in the model, and that's
Well,
why
actually,
you have when you talk about state noise, that the noise related to the measurement coming from the inertial measurement.
Yes.
No, it's not from the measurement. No, it's from the joystick. We have a joystick, and we commanded the robot with the joystick. And so, what is the state noise is that if I say the rod goes straight, and I just put the joystick straight, it's not actually going to go straight exactly. It's going to go a little to the right. And that's the
Open
problem.
loop, sort of open loop noise. It's not this noise. It's not the measurement coming from the.
It comes from the joystick. We take the entrance, well, the output of the joystick, which are the entrance of the robot. And we see experimentally that it's not, the noise is here taken experimentally.
We don't measure the speed of the robot. There is no Doppler system inside. So the input here will be the value of the joystick. But in practice, most of the time, the robot will have a log Doppler, and they will know the speed, and the input of the state equation will be the speed of the robot.
Yeah,
And also the acceleration and everything that is measured by proprioceptive sensors, such as the unit central and the Doppler.
Because at present time, everything is done outside the
Yes.
robots. And in reality, it will be autonomous platforms. So with the software running in the robots, and the noise will be not anymore the noise coming from the joystick, but the noise
From proprioceptive sensors.
yes, proprioceptive
And Doppler.
sensors. And in this case, the value of the noise will be completely different. The amount of the noise we will have,
Yes, but the
because
principle is the same.
at present time it is related to the joystick characteristics.
Yes.
And if you have very precise IMU, or it will be completely different. So
Yes.
the size of the boxes will be completely different. And
That's what I
But the principle
so
is
the next step is to have autonomous robots with the software embedded.
Yes, the next step.
And you have
Yes.
you have computer inside.
Actually, we have a social competition soon, so we plan on integrating that actually in the robots
For September.
for
No.
July.
First July.
So 2 weeks.
Lot of time.
3 weeks.
3 weeks.
Any other questions? So let's have a conversation.